electron in atoms. So this is the outline of this talk, and at the same time is a history of attosecond science, starting actually in 1987. So I will give the background and tell you about the first discovery, some progress, measurement of attosecond pulses that was very, very important. And let me acknowledge my two co-laureates for this Nobel Prize, Pierre Agostini and Ferencross. And then I will very briefly talk about applications. So nothing would have happened without the invention of the laser in 1960 by Theodor Meinmann. You have here a picture of one of the first lasers, a ruby laser. And the Nobel Prize for the laser went to the basis of laser, to Towns, Basov, and Prokhorov. And the properties of light that we will use are the fact that we can confine the pulses in short intervals of time, and the fact that it's intense radiation. The invention of the laser opened several fields of science, and one of them is nonlinear optics that started almost immediately after the invention of the laser. Here you have a picture of the experimental setup used by Peter Franklin in 1961 to demonstrate second harmonic generation. So you have here a ruby laser, again, focused into a crystal of quartz, and then you have a prism to disperse the radiation and a detector. The experiment I'm going to talk about during this talk will look almost like this, with instead of a quartz crystal, we will use gas. And in this experiment, he showed the second generation, where you create new frequencies using the laser frequency. You absorb 2 photons from the laser and you emit the second harmonic. Nobel Prize for nonlinear optics went to Nicholas Bloomberger, that you see here, and this was a Nobel Prize for laser spectroscopy together with Art Shallow. And in the same Nobel Prize, you have Kai Sigman. This is a Swedish physicist, and this is for high-resolution electron spectroscopy. And it's interesting to mention that here, because electron spectroscopy is going to be the very important detection method in our research. The other field that was started by the invention of the laser is atoms in strong fields or multi-photon processes. Here you have a simple 2-photon excitation process. So an atom absorbs 2 photons and is excited. And these processes were actually theoretically predicted by Maria Goppert-Mayer in 1931. If you increase the laser intensity, you can get multi-photon ionization. These were studied by actually Russians in the 60s. In 1979, Pierre Agostini and co-workers observed the phenomenon of above threshold ionization, where an atom can absorb more photon than what is strictly needed for the ionization. So here you see that an atom absorbs 1 more photon, and this leads to 2 electron peaks in the electron spectrum. In my thesis work, now we go to the beginning of the 80s, I studied multiple ionization of atoms by multi-photon absorption. For example, here, double ionization of xenon atom. At this point, we thought that to continue study this, how atoms behave in strong laser fields, we would like to look at the light that were emitted from these excited atoms or ions. So we set up an experiment to look at actually the fluorescence light. And here is the scheme of this experiment that was performed at the end of the 80s at Commissariat à l'énergie atomique in Saclay. So very similar setup. We have an intense laser pulse focused into a gas of atoms. We use a grating to analyze the radiation and a detector. And this is a picture of the laser that was used for this experiment. It looks rather old. It's a neodymium YAG laser, 1 micrometer wavelengths. This is the oscillator that you see here with two mirrors. And then we have 2 amplifiers. The pulse duration was 40 picosecond. And this is a picture of the experimental setup that was used. Laser is coming from the right. You have a lens here. This is a vacuum chamber, and inside you have a grating, and here a detector. We actually looked also in the perpendicular direction, because fluorescence is emitted in all directions. So we had also an arm here with another grating and another detector to look at light in the perpendicular direction. You can notice that we have a printer here, which is actually used to record the signal. This was a pre-computer time. So yeah, when you look at this picture, you think, things have actually progressed during 40 years, almost. So what did we see? We saw nothing in the perpendicular direction, so I'm not going to present that. And we actually didn't see fluorescence, or almost nothing. But what we saw instead was the high-order harmonic generation. And this is one of the first spectra you observe here obtained in argon gas. You can see harmonic 13, 15, up to 31. And when you plot the distribution of these harmonics, you see a very characteristic behavior with the first decrease, which was expected, but then this plateau, very long plateau, which ends up with a cutoff. You can see that I'm only odd order harmonics, and this is due to the symmetry of the interaction. It's central symmetric interaction, so that there is no even harmonics. Why is the plateau new? And this was unexpected and actually very exciting. That's because we were really thinking in terms of perturbation theory, where you can write expansions of the polarization induced in the medium in terms of the powers of the electric field. And for such an expansion to be valid, you expect the first order to be much larger than the third, much larger than the fifth, etc. And obviously this was not true because of this plateau behavior. So if you look at the electromagnetic spectrum, in this process we start from the infrared and we go to the extreme ultraviolet region. So just below X-rays. And a little bit for people here that are non-physicists, you can really make an analogy between harmonics, which are in music instruments, and harmonics emitted by this gas of atom exposed to a strong laser field. This is a spectrum actually recorded by one of my previous students, Christoph Heil, who was playing violin. This is actually alto violin. And you see that you have not only the tone that is excited, but many overtones. And so in both cases, you can interpret this as a strong interaction here between the string of a violin and the bow, and here between the atoms and the laser field. But of course, in one case, these are harmonics of sound. In the other case, we talk about harmonics of light. How do we interpret these results? This phenomenon, high-order harmonic generation, implies both the atomic physics, atoms in strong laser field, and nonlinear optics. So in order to understand it, we need first to understand the single atom response, which is described by the Schrödinger equation for an atom in presence of a laser field. and you have this equation here with the atomic potential, and this is the laser-atom interaction in the dipole approximation. And it's good enough to describe the light field as a classical light field. The difficulty in solving this equation is that the two terms are comparable, so we are really in a non-perturbative regime. And actually, the first attempt to solve this problem was to do it numerically. But you also need to understand the response of the medium to the radiation. In order to have efficient harmonic generation, you need all of the atoms in the medium to emit in phase. You need a certain phase matching condition to be fulfilled. You need here the small waves emitted by all of the atoms to be reasonably in phase during the medium. And this is described by Maxwell equations of electromagnetism, which can be simplified to a wave equation as this equation. Here you have the field generated in the medium due to a polarization, due to this single atom response. You can also make a small analogy to music again here. You need all of your atoms here, and I'm talking about really trillions of atoms to emit at the same time. It's like a gigantic orchestra, and in the same direction. So the first attempt to explain, interpret this phenomena was to actually solve these two equations that I just showed you. This is a calculation by Canculander and Brusher in xenon. So this is the single atom response, and you see that it fits with the experimental result. In a way, this result was surprising in itself, because at the time we thought that phase matching would be much more difficult to realize for the higher orders. So it was important to solve the second part of the problem, which we did a couple of years afterwards, and this is some calculation, so solving both the wave equation and the Schrödinger equation, showing that yes, we could reproduce more or less this plateau behavior. This is results obtained in xenon at different laser intensities. So we can reproduce numerically this result. Doesn't mean that we understand the physics. This would come afterwards. But at the same time, now we are in the beginning of the 90s, came the question, is it possible that this radiation lead to the formation of very, very short light pulses attosecond? And the idea is simple and is presented here. I'm showing here three different waves corresponding to three different harmonics. So let's assume that these waves are phase-locked, which means they are in phase at a certain time, like the maxima happen at the same time. Because of the periodicity of the problem, then half the laser cycle afterwards, the minima will be in phase, and then again the maxima, the minima, etc. So now let's add these waves together. You can do that in your head. And what do you get? You get constructive interferences when they are in phase and destructive interference when they are not in phase. And you get a series of very, very short light pulses. You can plot the intensity of these pulses, and you get really short pulses in the range of 100 attosecond. So, and if you add not only 3 harmonics, but let's say 10 harmonics, you can get even shorter pulse. It's just an expression of a Heisenberg principle. If you have a broad bandwidth, then you can, in frequency, then in the time domain, you can get very short pulses. So the question was, are these harmonics phase-locked? And this was a question that is going to be debated during more than 10 years. Why was this so exciting? It was very exciting because the research towards very short laser pulse had come to a stop of the order of a few femtoseconds, as you can see on this diagram. This is the progress of ultrafast optics towards shorter pulses using dye laser, and then the titanium sapphire laser. The stop is a few femtoseconds. Why is this stop? This was even called the femtosecond bar. The stop is simply due to the frequency of the light. In order to have short pulses of light, you also need to have high frequency, because otherwise you are limited by the optical cycle of this light. So you need high frequency to have a short optical cycle. And of course, as I said just before, you also need a broad bandwidth. So this was very, very exciting, but the question was, are the harmonics phase-locked? Now I'm coming to part 2, progress in technology and in understanding. So now I'm in the 90s. And let me start by progress in technology. This field has really been driven by laser technology, and the progress in laser technology has really been very, very important in our field of research. First of all, beginning of the 90s, there are 3 discoveries in laser technology. The invention of the chirp pulse amplification, leading to a Nobel Prize to Gerard Moreau and Donna Strickland in 2018. You have a new material, titanium sapphire, discovered by Peter Britton. And then you also have a new technique to produce short laser pulses from an oscillator called Kerr-Lenz mod locking. And 3 scientists here looking at this new technology, and they decide to buy the first prototype amplified titanium sapphire laser in Europe. This was very risky because no one had done that before, to put all of this invention together, but it was really a very good decision from them. So they built this terawatt titanium sapphire laser system in Lund, and soon afterwards they created the Lund Laser Center. At the same time, back in France, in Saclay, we are building dedicated instrumentation to study high-order harmonic generation, with more or less the same ideas I showed you before: gas jet, optics to analyze the radiation, and then a detector. And this looks like this. This is actually me, long time ago. And my first 2 PhD students in France. And we built this instrument that you see here with the gas jet here. The laser is coming from the hole here, and optics in this chamber, and detection here. This is the time where computers arrived in the laboratory, and this really changed the way to do experiments. The computers look like this, with floppy disk, but we started writing programs to acquire data. So this was also a big improvement. So the Swedish scientists that you saw on the previous slide asked me if I would like to come to Lund to do experiment and bring this equipment that you see here together with my students, actually, and do some joint experiments. So this is what I did in '92. We did a very nice experiment. This is one of the spectrum obtained in helium, where you see really high order harmonics up to 93. And this is another result obtained in neon, where this time we can really start to study high order harmonics as a function of the different parameters of the problem. And we can do that because of 2 reasons. First, the relatively high repetition rate of this laser, 10 Hertz, much better than before. And also because of this fact that we could use now computer programs to treat our data. So a couple of years afterwards, I actually came back to Lund for private reason to share my life with my husband, and this is the time where I switched countries. About this time, huge progress in understanding with Thanks to theorists, I'm showing to you mostly experiments, but theorists have been very important in this field and the interaction between theorists and experimentalists. And here you have Ken Kullander, Ken Schaefer, Paul Corkum proposing the very intuitive picture of what is happening, called the three-step model. And here Maciek Lewenstein, Misha Ivanov, proposing a quantum formulation of this model. It's called the strong field approximation. It's very important in our field. And this is this three-step model, so I'm going to describe it, and then I will propose, this is mostly for first, second-year students, if you are not used to this, an analogy of this model. So, what you see here is atomic potential, which is deformed due to the laser atom interaction in one direction during a certain time. And now you have a potential barrier here, and we are within quantum mechanics. The electron that you see here in the ground state has a certain probability to tunnel through this barrier. Then the electron is driven by the laser field. We're talking about a few nanometers, so much more than the dimension of the atom. The laser field change of sign, so the electron is pushed back towards the atom, and there is a certain probability for recombination back to the ground state. If you consider the different electron trajectories, you see that the electron is coming back with certain different kinetic energies at different times, and the corresponding light emission that you have in this process is approximately that of an attosecond light pulse. This is a fully coherent process. You can also think of it as an interference effect between the wave packet going out and coming back and what is left in the ground state. So now I promise you an analogy, and this is called the electron. This is in Swedish, but it's very easy. You just replace C by K. And you remove the double dots. So this is called laser adventure in a laser field. Okay, this is just, you have an electron which is strongly bound to an atom. This is a strong force, and it's good because otherwise we would not exist. And then you have a strong laser interacting with this atom. We can represent this as follows. This is an electron in a prism, and on the side is a roller coaster, amusement park. So the electron is looking at this, would like to escape. How does he escape? He or she? This I don't know, but how this. Now I'm asking students here, how does the electron escape? Come on. Oh, you're too shy. Yes.
I'm not sure, but as the roller coaster approaches he or she who's in that prison, as the roller coaster approaches, it will make the person that's inside for a quick moment go out of the prison, but then go back to the inside.
Yeah, but how does he escape? Yes.
He makes a tunnel and goes out?
Yes, he makes a tunnel. Yes. Of course. It's not finished. Wait. Next step, the electron is free, and he has fun. He's going down and up in this roller coaster. It's being accelerated. I'm translating to you in the laser field. This story is finishing very badly. And this is it. unfortunately, the electron is meeting the open prison and is falling and screaming. And this is your light pulse. This is the end of the adventure. Yes. Okay, I'm continuing. This is more experimental progress. Now we are at the end of the 90s. This is an experiment that we did in Lund together with Mette Gård. She was my first PhD student in Lund. Ted Hensch, Nobel Prize laureate in 2005. Marco Bellini from Florence. This was a European collaboration. This is myself and Klaus-Johan Wallström, Claire Lingo. There were several participants. And we looked at the coherence of high-order harmonics. And to do that, we make two replica of the harmonic pulse, and then we look in the far field and see whether these two sources created by the same laser interfere with each other. Simple experiment. Of course, in between here, we have a grating to separate the different orders. This is what we saw for harmonic 15. You see very nice interference fringes. Great, this light is fully coherent. What you also see is two regions, a collimated beam and a more divergent beam. And this was really the first experimental confirmation of this three-step model that I just presented. There are two families of trajectories. Short trajectory where the electron is coming back immediately, and long trajectory where the electron is doing this. And it takes longer time to come back. So you can see on this picture. And the reason for the different divergent property is related to the accumulated phase of the electron on its trajectory, which is very different in the two cases and which affect the wavefront of the radiation. You can say that it was great confirmation of the three-step model. At the same time, the nice temporal structure that we hoped the harmonics had with this train of attosecond pulses was a little bit ruined because of this result, because you have this short and long trajectory, so there are actually more temporal emission during this process. So, but at the same time, you can also immediately see a way to control these trajectories by putting an aperture in the far field, and, for example, here remove the long trajectory. And this is what Pierre Agostini is going to do in his experiment that I'm going to show in a minute. So more understanding. Maybe this is not as simple as we think with the temporal structure. But we know how to control this now. So also, to finish now the end of the 90s, huge progress in laser technology. Now people learn to make very, very short pulses using post-compression techniques, in particular the hollow fiber compression technique that was discovered by Moronizoli and co-workers in Milan. And also, the concept of the carrier envelope phase become important, and the carrier envelope phase is the difference between the peak of the envelope of a pulse and the maxima of the oscillation of the laser field. So now people start to learn how to control and to stabilize this carrier envelope phase. So now I'm coming to part 3. I'm going only briefly to present the measurement techniques used by Pierre Agostini and Ferencross to measure this attosecond pulse. This was a very important step because, as I explained, we knew that we thought that there was attosecond pulses, but in some conditions, but it was really important to measure their duration. And in both cases, they use a cross-correlation technique, which is explained here. You generate attosecond pulse in a gas, And then you have a probe field, which is here. So it's a cross correlation between attosecond pulses and a laser field. And this cross correlation is performed in another gas medium. And what is detected is the ionization of the gas and especially the energy of the electrons. And you can see this is some first results by Pierre Agostini, and then in Vienna, Garching by Ferencross. These are further results obtained a little bit later in Milan, and the present record is 43 attosecond. This is a result obtained in Zurich. You can see that it's very much European, so research has been really driven by, I think, by European laboratories, has been helped by instruments from the European Union, networks, access programs. I think big thanks to the European Union for this research. So let me go a little more in detail into the measurement technique of Pierre Agostini, which is a very nice technique called RABBIT, which means reconstruction of attosecond beating by interference of two photon transition. And it's based on an idea by a theory group of Alfred Mackay. And this is the idea here. First, let's look at a two-photon process using a harmonic Q and then a photon. So this leads to two electron peaks with different energies. And this is called the main peak or main band, and this is called the side band. Now you can also two photon by absorbing the next harmonic here and emitting one laser photon. This is stimulated emission of radiation. Now you see that you have two quantum paths leading to the same final state, leading to this sideband. And we are doing quantum mechanics. We add the amplitude of these two quantum paths. And the amplitude of these adding the amplitude, of course, is going to depend on the relative phases of these two quantum paths. So let's look at the phases. First of all, you have I'm missing one here. Yes, you have the phase of harmonic Q, and there are actually two contributions here. One due to the harmonic field, which is what I want to measure, and there is an influence of the ionization, which I'm going to neglect first. It's a small contribution. This is going to be very important for application later, but here let's simply neglect that. Then you have the phase of the other harmonic, and you have a contribution from the laser absorption or emission. There is a delay between the laser and the harmonics, so the phase is omega tau, and here it's minus omega tau because it's an emission process. So the interference signal looks something like this. You have the cosine here with the phase difference, so it's phi q plus omega tau minus phi q plus 2 minus omega tau. So you see, but simply by looking at this interference signal as a function of tau, you can deduce the phase difference between consecutive harmonics. And this is what I want to measure because I want to check whether phase locking is achieved or not. And this is what Pierre Agostini did, and measuring this phase difference and together with the intensity of the harmonic from these intensities and spectral phase variation, he could go in the time domain by Fourier transform and reconstruct the pulse train, and this is the result showing a pulse train with attosecond pulse of duration 250 attosecond. Very briefly, the technique used by Ferencross. So Ferencross used very, very short laser pulses of the order of 5 femtosecond, and he could measure isolated attosecond pulse. This is one of the first results, which I'm not going to comment because it's not so clean, but this is a later result where you have a very nice so-called streaking trace. So the technique that he used is also cross-correlation, is called streaking, and the idea is simple. You ionize the atom with your attosecond pulse, you create an electron with momentum pi, and then this is happening in presence of the laser field, so the electron can gain or gain extra momentum due to this laser field. So extra momentum equal to minus EA, the potential vector of the field. And in some case, the electron can gain energy or lose energy, and you get this streaking trace here. And from this trace, you can recover the pulse duration of your attosecond pulse here, 250 attosecond. So now I'm moving to the last part of this talk. I'm going very briefly to present some application, going a little bit from very basic research, very fundamental, to maybe more applied research. And let me start by talking about electron motion in atoms and molecules. This is the promise of this attosecond light pulse, is to follow motion of electron. This is the right time scale. This is just a picture of an atom in the framework of Bohr's atom model. This is a picture of Niels Bohr. And if you calculate the time for an electron in this model to go around the nucleus for a hydrogen atom, it's 150 attoseconds. So this tells you that this is the right time scale. Now, of course, this is not how it is. We are quantum mechanics. You don't have a small ball going around the nucleus. It's more like a wave. So this we cannot see. But something we can try to measure is the process where, for example, an electron is ionized. This is the photoelectric effect, which was explained by Albert Einstein in 1905. So let's look at photoionization process. What can we measure? Well, we can measure, for example, the time it takes for the electron to propagate in the potential, and if there is a difference between ionization in the 2s state in neon or in the 2p state in neon. How do we do that? We used again this beautiful interference rabbit technique that I presented. So what you see here are what is called rabbit trace, oscillation of the electron spectra as a function of the delay, and these are sideband peaks that you see very nicely oscillating. And here we compare this oscillation in the 2s shell and in the 2p shell. You can make a small analogy with music again. We are measuring time scale or times by measuring where the maxima of a wave is. And this is really like a tip of a metronome doing like this, making a wave motion, and this is how you can determine the pace in music. This is time. You can also represent that on a clock. In this measurement, 1 hour in a clock is half a laser cycle, so it's 1,300 attoseconds. This is a titanium sapphire laser. And what we are able to measure in these experiments is the time difference. So the position of 2 arrows, we don't know where these 2 arrows are. They are anywhere on this clock, but we can measure the difference between the 2 arrows. And this is a result showing here a difference in delay between 2s and 2p ionization. And you see that it's we are reaching precision of 20 attosecond or so. And this is a comparison between theory and experiment. This is another example where we look at 4D ionization in xenon. where we measure this time. So it's the absolute time delay. We calibrate our experiment by comparing helium ionization, or actually neon ionization and xenon ionization. And in this case, you see that we have a positive time delay. And in this region, this corresponds to a phenomenon in atomic physics, which is called a giant dipole resonance, where the electron is trapped on its way out. And this leads to this time delay. And here you have even long time delay, which we interpreted as due to a spin flip in this process, so due to the spin-orbit interaction. It's just to show you a little bit what we are able to do. And really the challenge of attosecond science now is to extend these techniques to more complex systems, bigger molecule or condensed matter. Very briefly, I would like to say that there is also application to industry now, which are coming out, and in particular to the semiconductor industry. And now this is an application not too much of the attosecond pulse structure, but simply of these high harmonics, which are in the extreme ultraviolet range and very, very broad band and many frequencies. And the idea simply here is to use diffraction on integrated circuits on a wafer here, and to look at the reflection from the diffraction from this wafer at different frequencies, and to deduce, to be able to check if this wafer has defaults or not. So, as you know, this is important for the next generation computers, smartphones, is to be able to reach a dimension which are of the order of 10 nanometer. So the technique for lithography of circuits in this range now is based on actually light from thin plasma. But there is no good technique yet for the metrology, checking defect on this wafer, and this is where the high harmonics are a good candidate, and there are prototypes being made at the moment. Now I'm really coming to the end of this talk. Next chapter in attosecond science is really to open these techniques to broader fields, to chemistry, possibly biology, condensed matter physics, also application in quantum physics. There are also new attosecond sources arriving from free electron laser, and this will be very interesting because they have different characteristics. They are more in the X-ray range. It's much easier to make, actually they only make isolated attosecond pulses, and they are much more energy. Okay. If you are a little bit lucky, as I've been, to be a little bit at the right time, the right place, many years ago, 37 years ago, you might end up here. This is in Stockholm on the 10th of December last year. And so what you see here, these are the Nobel Prize laureates. I'm here. And this is the royal family in Sweden. And you have academy members, and it's a very nice ceremony. And you might be happy to receive a medal from the King of Sweden that you see here. After this ceremony, you have a banquet, a huge banquet in the City Hall in Stockholm. And this is the honor table. I'm here. And coming from France, it's an experience to sit during 4 hours close to the King of Sweden. You need to be a woman to be in this situation. Nobel Prize winner and woman. But if you are a man, you can sit together with the Queen of Sweden. So, okay, I would like to thank you. This is my research group. Of course, I've been collaborating with many people over the years, and this is my research group celebrating this Nobel Prize on the 10th of December. This is why they are dressed up like this. And I would like to thank a very nice collaboration with University Porto and Sphere Ultrafast Photonics. This is a picture of actually people working together. And you have people from Lund and from Porto University / Sphere Ultrafast Photonic in blue here. Paulo, Helder, Rosa, Miguel, they are all here. And let me end by thanking University of Porto. Thank you.
I think we have time for a few questions. Don't be shy, please, and just, yes.
Yeah. You mentioned the streaking technique when
Hold on.
When you were talking about the first measures of attoseconds, you mentioned the streaking technique.
Yeah.
I didn't understand well how it affects the measurements.
I can go back to the picture. Yeah. The idea is you create an electron by absorption of XUV radiation, and then you move this electron by a laser field up or down, meaning momentum. And if if the XUV pulse is very long, you are not going to see anything. But if the pulse is very short, which means the electron is created at a certain time of the laser cycle, then you will see an increase or a decrease of the electron momentum that you detect. This is this streaking technique. And the measurement consists of then recover from this trace the pulse duration. So the shorter the pulse, the sharper this trace is.
Thank you so much for your presentation. It is really inspiring. Yeah, my name is Maya. I have one comment and one question. So the comment is like, it took you like 10 to 14 years in order to do a measurement, in order for scientists to do a measurement of these poles. So with that being said, my question is regarding some pressure that, for example, people have to publish papers and to do science. So I wanted just for you to speak a little bit about that and what is your feeling regarding this and regarding the 90s and today?
Yeah, I think this is a very good question. This was a difficult period, actually, end of the 90s. We were discovering things, but we were really fighting with this measurement. We had ideas, but they didn't work. And this idea, which was come from this group of theorists in France, it was buried in a big paper. So it was not so well known. It's only Pier Agostini that had seen that and was trying. It took him many years. So I would say basic research is based on persistence, persistence by actually many researchers. And we could continue afterwards thanks to this measurement by Agostini and Cross that happened in 2001. So this end of the 90s, I was actually a little bit asking myself, well, maybe I should change research field. It was a difficult period. So yes, persistent is important, and I would like to say that basic research takes time, and somehow our people financing this research and giving grants to they have to understand that. I'm trying to say it. All my talks, I'm trying to show that it took time for this research to arrive to something useful. Let's put it this way. So, and it's important to have enough time. I think it was possibly a little less stressful in the 90s than now. Now maybe it's a little bit too much, yeah, publish or perish or something like this. Publish intermediate results. This would be my advice.
Hello, I'm Diogo. Thank you very much for your talk first. I want to ask, you showed a graph before on the harmonics, where on the experimental values you can clearly see that there was the plateau and then the cutoff.
Yeah.
But there was a small discrepancy between the theoretical and the experimental values.
I guess I have to go back.
It was little.
Here?
Exactly, yeah. On the values of 15 to 21, there's a small discrepancy between the experimental and the theoretical values. I would like to ask if there's any specific reason or...
I don't. These were very early calculations. I think now people can do much better calculation. This would be my first answer. One interpretation is phase matching, but I'm not sure we really manage here. I don't know. This is a very early calculations. I mean, at this time, I can make another comment. At this time, to agree within one order of magnitude was good. I can tell you that nowadays, especially with the collaboration that we have with this company, ASML, so we are interacting with them. They are asking us about the sources, not about the technique, but about the sources. They want to know how many photons we have in absolute value within a factor 2 or even less. So we are actually pushed to do much better measurement and really give results and predictions. Nowadays, I think the simulations are much, much better.
Thank you.
We have over there.
I have a couple of questions actually about the last topic, the last part of the... okay, I'm sorry. I have a couple of questions actually about the last part of the fourth topic. Is there been any attempts in modern physics of using the autosecond method for studying another particles, or has autosecond showed a way to study, for example, hypothetical particles like the graviton, or it has been also used to explain antimatter, or study other kinds of particles?
I would say, spontaneously, I would like to say, unfortunately, no. I think there are different timescales for different particles, but the future belongs to you. You're welcome to have very clever and good ideas. But I would like to say that we cannot access timescale like proton or neutron and graviton. I don't even know if this exists. but yeah, again, think out of the box. Yeah.
Okay, I think this is the perfect place to finish. So thank you, and
thank you.
In the name of the team, I'd like to offer you this. Thank you.
Martina was in a jury, in an academic.
This is a student. Yeah.
She was in an academic.